Hi everyone, Mrs. Basega here, and today we're studying for Unit Three's test. In case you haven't done one of these before, remember, I'd like you to try all these problems first, then check the answer key, and only watch this video for the questions that you got wrong, or that you're struggling with. I don't intend for you to watch this end to end. Not only that, but I want to point out these objectives. These objectives mark all the things I'm going to ask during the test. A really good idea for you then is to go through and think to yourself, can I tell apart the difference between rotations and revolutions? If so, check yes. If you're able to do these things, you can be reasonably assured that you're going to do just fine on the test. So let's get started. In number one, we've got an 800 kilogram car driving on a circular track. It says to draw and label three vectors, one for centripetal force. And centripetal force should start at the car. And centripetal means center seeking. So I'm going to draw an arrow that points towards the center of the circle and label it FC. I need another one for centripetal acceleration. So I'm going to start at the car, draw another arrow, and label it AC, centripetal acceleration. And last, I need one for tangential velocity. I'm going to start at the car and draw a straight line in the direction of motion. I'm going to label it V for tangential velocity. That tangential velocity direction is important because if the friction force fails, this is the path my car takes because of inertia. Some things to point out for vectors. They should start at the object you care about, they should be labeled, and they should be straight lines. If you just gave me three arrows, I wouldn't know which ones you were talking about, so make sure you label your vectors. I had mentioned that friction provides the centripetal force on the car. And the way you can think about this is actually think about this car from the side. If I were looking at this track from the side, the centripetal force is the one that has to point towards the center, the force pointing to the right. If this were the car with its little wheels, gravity would point down, that's not towards the center. Normal force would point up, that's not towards the center. That leaves only the applied and friction force. I said friction force because it's the friction between the tires and the road that allows the car to turn. Actually, if you want even more evidence here, imagine what would happen if we tried to make this turn on ice. If the friction force were not big enough, my car would just go in a straight line along its tangential path because its inertia carries it in that direction. Now, in this case, it says calculate the amount of centripetal force. And as you go through your equation sheet, we've got the choice of mv squared over r can be solved for force. We could use a net force equation, but this one makes more sense to me because I'm given the mass of 800, the speed of 25, and the radius. This is calculating me the value of the friction force. If the friction force is not at least 2,000 newtons, then the car is unable to make this turn. Now it says calculate the new centripetal force if the track has twice the speed and 2 times the radius. This is a proportions problem, and I can tell because I'm trying to compare one situation to another. My original car had a speed v, but now I'm putting in twice the speed and 2 times the radius. Notice that in the denominator, when I apply the distributive property, this reads m2 squared v squared over 2r. When I do this, I'm making sure that I distribute the 2 to both variables inside the parentheses. Now, rearranging, this means I have 2 mv squareds. I have 2 times more force than the original force. So if the original force was 2,000, my new force is 2 times 2,000 equals 4,000. This makes sense because if I am driving faster, I need more friction force in order to make this turn. Now, it actually doesn't matter whether I'm asking about C or D here. This car can only exert a friction force of 1,200 newtons. That doesn't meet either of those requirements, even if I was going in the smaller and slower track. If the friction force is 1,200 newtons at most, that is not enough to make this 2,000 Newton path. So can the car successfully make the turn? No. 1,200 newtons is less than 2,000 newtons. Therefore, it's just going to go along its tangential path. It's going to go in a straight line. It's not going to be able to make the turn, so it's going to go along the green path above. Now, I'm going to come back in the answer key later and write these out in more detail, but this is just so that you're not sitting here watching me write. Feel free to read a more in-depth explanation in the actual answer key in Google Drive. So in F, Aiden is in the passenger seat and is moving around this curve. They feel like they're getting pushed outward against the door, and they claim there's a force pushing them outward away from the center of the circle. I disagree. And the reason I disagree is that in both our free body diagram here and our vector diagram here, there's no forces going in the centrifugal direction. Centrifugal means going away from the center of the circle, and there's no forces going out here. In fact, if I'm trying to make a right-hand turn, why would I put a force in the left-hand direction? What's actually going on with that is Aiden feels like he's going in a straight line. He's going along the tangential path, actually. So as the car moves, a moment later, the car would be here. But he's gone in a straight line. So his inertia going along that tangential path keeps him going in a straight line as the car moves right. There's no centrifugal force towards the outside of the circle. This is an effect of inertia. It's called the centrifugal force effect. I also disagree with Sophia. Sophia says the car is not accelerating because the speed is constant. This is not true. Whereas there is an acceleration that's equal to the change in velocity over change in time, I want you to notice that velocity is a vector, which means it has both magnitude and direction. While the linear velocity isn't changing, it's not speeding up or slowing down, you do have a centripetal acceleration. This is the acceleration that causes a change in direction, even if the velocity magnitude is constant. It causes a change in direction because sometimes the car is going left, sometimes the car is going right, but that changes as the car travels. There is a centripetal acceleration even if the speed is constant. Ah yes, a merry-go-round. We have three students, A, B, and C, on a merry-go-round. The difference between rotating and revolving is where the axis of your system is. So A is on the axis. If you're on the axis and you're rotating about what's called an internal axis, that little dotted line goes through our student Andy. Andy is rotating because the axis goes through his body. But both Bob and Chuck are revolving. They're revolving because the axis is external to them. Not only that, but if we think about it, rotating things travel no distance. They just move about their own internal axis. But revolving things, well, these are going to travel in a circle. So Bob travels in a circle. Chuck travels in a circle. These both travel some sort of distance. Question B asks for time period. And we have the choice of this total time versus number of cycles equation. We could also do velocity is 2 pi r over t. And a common thing I do is I think of all the equations that have a capital T for time period in it and cross out the one I don't get to use. I don't know the velocity, so I can't use this. I must use this first time period equation. The total time is 32 seconds, in which it makes 8 revolutions. So it takes 4 seconds per revolution. 4 is the time period. Notice for this, I just kind of assume that you know what symbol goes with what. you need to know off the top of your head the time period symbol is capital T, and that for things that are attached together, like Andy, Bob, Chuck, and the merry-go-round, all have the same time period because they're attached together. Think about it. Andy can't complete a circle before Chuck does. They have to go at the same time period because they're literally attached to each other. But their tangential velocities could be different. Tangential velocity is what we did with the Flying Pig lab. So we're calculating 2 pi r over t for Andy, Bob, and Chuck. But hey, when I do this, Andy has a velocity of 0. When Andy is in the center, he has no radius. And that no radius means he travels no distance. Even if I substitute in here, I'm not going to get a number because it's 2 pi times 0 over 4. That gets me 0. Andy doesn't travel any distance because he's rotating. At the same time, Bob is 1 meter from the center. So doing my substitution here, that's 2 pi times 1 over 4. This gets Bob's speed as 1.57 meters per second. Chuck is twice as far out as Bob, so he should have twice the speed. And lo and behold, when I do this out, Chuck's speed is 3.14 meters per second, twice as fast as Bob. For centripetal acceleration, there's only one equation that makes sense here. So each one, I'm just going to substitute in the speed from earlier, their radius, and calculate. Andy's speed is 0, and the radius is 0. If you're having trouble with this in your head, you can imagine this as doing 0 squared over 0. The 0 on the top cancels the 1 on the bottom to just give 0. I know, it's tricky, but there's 2 zeros on the top and only 1 0 on the bottom, so the 0 on the top dominates. I promise you'll learn it in calc. Alright, guys. So it takes no centripetal acceleration for Andy because he's at the center of the circle where both his speed and radius are 0. Bob, however, has a speed and a radius. This gets 2.46 meters per second squared. This is the acceleration that shows he is changing direction. Similarly with Chuck, I'm just substituting and solving. He's got a speed of 3.14 meters per second, a radius of 2. This gets an acceleration of 4.9. So comparing Chuck to Bob, Chuck is going twice as fast and requires twice as much acceleration. As a result, Chuck needs to have the largest applied force in order to stay on the ride. Centripetal force can be calculated with mass times centripetal acceleration. So assuming they're all the same mass, or at least close enough, well, Chuck would have to use twice as much force because he has twice as much acceleration. He's changing direction at a faster rate because he's farther out from the center of the circle. Chuck would need to apply twice as much force because of this direct relationship. And needing twice as much force, if he doesn't apply that amount, then he goes sliding off this merry-go-round. So this problem is pretty cool because it is true. So I want you to imagine this lunar gateway as a space station above the moon. So we've got our moon, and orbiting the moon is going to be this space station, the lunar gateway, LG. Because they're orbiting, there's a centripetal force. LG, the lunar gateway, is attracted to the moon. But gravity is a force. It's an interaction between these two objects. So both objects have to experience the same amount of force. This is actually Newton's third law. Because the force is an interaction between two objects, both objects experience the same amount of force. This isn't comparing the moon to the Earth, so it can't be D. There's definitely a force of gravity acting on the lunar gateway, or else it wouldn't be doing its little cool orbiting thing. So I see there's a typo in here, and I'll have to correct this in class. But let's say that it's going to be D. The force on the moon is equal to the force on the lunar gateway. We'll fix those options in class. In B, it asks for a velocity in order to orbit. That's going to kind of hint that I want this orbital velocity equation. However, if you did think of using this velocity equation, I want to point out that we don't know the time. So while it's a good guess because it has a v for velocity in it, you're not actually going to be able to solve that. So I see v squared is related to this gravitational constant. So I'm putting in 6.67 times 10 to the negative 11th. For m, I need the bigger mass, only the mass of the moon, not the mass of the space station. The reason it's a capital M is I want the bigger of the two masses. And finally, orbital radius. All of that gives me 70,035, but I do want to point out that that's not v, that's v squared. So if I want to solve v by itself, I need to take a square root of both sides. Plugging that into my calculator gives a much more reasonable 264 meters per second. This sideways velocity, the 264, 265 meters per second, is why the lunar gateway isn't going to crash into the moon. It is falling towards the moon, but it's moving to the side. In fact, the astronauts are floating around. This is because there is gravity in space, but that the gateway and the astronauts are falling at the same rate. It's kind of like if you were in the Tower of Terror ride. The ride is falling, you're falling. There's obviously a weight acting on you, but because you're falling at the same rate as your surroundings, you appear weightlessness. This apparent weightlessness means that the normal force is zero as you fall. D is a proportions problem. It's saying that I'm having a new lunar gateway, and it's going to have twice as much mass as it did before. The mass of the moon stays the same, and it's in the same place, so how would the gravitational force change? This is a direct relationship. Doubling the mass would double the force, so I would have twice as much. So now I'm taking this heavier, more massive lunar gateway, and now the crew members are asking about the speed. I agree with Alice. The reason I agree with him is that this speed is determined by the mass of the moon. That's why it's the capital M in here. It's the mass of the moon, not the mass of the space station. So doubling the mass of the space station doesn't change the mass of the moon, so the speed stays the same. But just to be more clear, Sean says it would have to have a higher speed. That's not true. Mass and orbital speed don't have that same relationship except for the mass of the central object. Tali's got a good idea, saying that more mass is harder to accelerate, but it was orbiting to start already. Because it was already orbiting to start, this is just the speed it needs to stay orbiting. It's not trying to have a linear acceleration. Proxima b and Proxima Centauri, this is the solar system that is closest to ours. It's only 4.2 light years away, but our galaxy is like, a few 100,000 light years across. So this is our very nearest neighbor. This planet is squarely within the habitable zone, which is kind of cool. For 5a, it asks for orbital velocity, and I bet you are really tempted to do this because we just solved this on the back page. But remember, any equation with v, if you have the correct variables, could be used. So I'm actually going to solve this one. I know the radius and time. The radius of this orbit is 7.5 times 10 to the ninth meters. And the time period is 1 million seconds. This gets a speed of 47,124 meters per second. But now I can use this speed to get the mass of the star. So I'm going to write down my speed equation, my orbital speed equation. This is going to get me the mass of the star. Because I know the speed is 47,124 meters per second, I can solve. In this case, I'm going to have to do some algebra here. The radius was 7.5 times 10 to the ninth, and I'm solving everything for m. So you know what? I'm going to plug this number into my calculator, this number into my calculator, and hope things simplify out. The velocity squared is a big number. I got 2.22 times 10 to the ninth meters per second squared. Then the number in the parentheses on the right was 8.89 times 10 to the negative 21, all times m. So to get m by itself, I'm trying to get rid of multiplication. And the way you get rid of multiplication is division. So I'm going to divide both sides by this 8.89 number. This gives a nice big mass. By dividing by an incredibly small number, the mass must be really, really big. I get a mass in this case of 2.5 times 10 to the 29th kilograms. That is huge. That's enormous. Like, that is over 10,000 Earths worth of mass, just for reference. I needed to be able to solve this one so that I could later calculate the gravitational force. Now, I want to point out there's a few ways you can do this. I can use the gravitational force equation, the universal law of gravity, or I could use mv squared over r. Guys, they both work here as long as you're picking the right thing. In the equation on the left, I need to put in my 6.67 times 10 to the negative 11th, mass of the star, and mass of the planet. Then I would need to do that radius squared in the denominator, the 7.5 times 10 to the ninth, all that term squared. So it might actually be a little faster to do the other one. And the reason I said you have to use the right mass here is notice this is the little m. It is the smaller of the two masses. I need to put in the mass of the planet here, not the mass of the star. So I'm putting in the 7.75 times 10 to the 24th kilograms. We had the velocity of 47,000, all squared over radius. Lo and behold, both answers give you 2.29 times 10 to the 24th newtons. Because gravity is the centripetal force, it doesn't super matter which equation you use as long as you use it correctly. Question D is asking to make a relationship between gravitational field and distance. The farther you are from your planet, the weaker this field should get. I'm choosing A in this case because I'm looking for what actually graphs this 1 over r squared relationship. The inverse square relationship should show a field that starts big when you're close and gets smaller and smaller and smaller the farther out in space you go. Now, the gravitational field equation in its entirety looks like this, but please be prepared to only use this to compare things to Earth. So in this case, G stays the same. This planet is 1.2 times larger mass and larger radius than Earth. So I'm putting in 1.2 m for the mass and 1.2 r for the radius. It just so happens that those are the exact proportions. Weird. It's almost like they might have a relatable density or something. Noticing this, when I sort the changes to the left, I have 1.2 squared on the denominator, and one of the 1.2's is going to cancel. 1 divided by a number greater than 1 is going to give a number less than 1. The gravitational field on the surface of the exoplanet is 0.83 times that of Earth's. So if I want to calculate this precisely, it's about 83% of Earth's field. So multiplying by 9.8 gives me 8.1 meters per second squared, or newtons per kilogram. Please note that newtons per kilogram and meters per second squared are the same unit. Now, for this one, I have 3 planets orbiting a star. It clearly looks like that's the Earth, but we're going to pretend that that's a star. Look how pretty that star is. Okay, so it says, what is the correct order for the average speed of the satellites? You know what this is getting at is it's getting at this orbital speed relationship. They're all orbiting the same star here, so the mass is the same. G is a universal constant, so that's always the same. So what this equation is really saying is the larger your average radius, the smaller the average velocity. So A is farthest out, this would need to be slow. C is inside, this would need to be fast. So comparatively, C is the fastest, then B, then A. So I said this choice here. Okay, so for number 6, I calculated the period squared divided by the radius cubed for all the ones I could do. That was Venus, Earth, Mars, and Uranus. And I want you to notice that because these are all orbiting the sun, these all have the same value just about for t squared over r cubed. So while I'm going to show you one way to solve problems B through E, the other way you could do it is noticing that this equation for Kepler's third law can be simplified. With the units that are given right here, the years and astronomical units, well, notice that this value ends up being 1 for everything that orbits the sun. So if I wanted to, I can just set these two equally to each other and solve one for the other. This is important if I ever have a value in this column that's not equal to 1. So I know on the homework we had one where the leading value was 0.022 or something along those lines. Whatever number is in this ratio of t squared over r cubed is what 4 pi squared over gm is equal to. So while you can go solve it directly, I'm going to show you the proportions way. So for the proportions way, notice that for B through F, all of these examples are comparing two things. In B, it's comparing Jupiter's orbit to Earth's. In C, Saturn to Earth. In D, satellite to Earth. To E, comet to Earth. If it's comparison, then I don't need to solve out this directly. If it's comparing two things and I just want the change, how does the radius affect the time, then I don't need to use this leading value at all. I can write this as the time period squared is proportional to r cubed. In this case, r is 5.2 times larger. So that's 5.2 to the third power. So t squared is proportional to 141. Taking the square root of that gives me t is 11.85. Now I didn't put units here because it's a comparison. How much longer is Jupiter's period than Earth's? So the period is 11.85 times longer than Earth. It takes Jupiter more time to go around the sun than Earth because its distance is farther out. So I can put 11.85 in the chart right here. And that kind of makes sense because we're going in order from things close to the sun. Cool, so this is just rinse and repeat. So for each one of these, I'm comparing two things. since I'm comparing two things, I'm going to be comparing t squared to r cubed, substituting, solving. Saturn's time period is longer than Earth's by 29.5 times. So if I do 29.5 squared, that's equal to r cubed. So on the left-hand side, that's 870 is proportional to r cubed. To get rid of a cube, I need to apply a cube root. So imagine I want to get rid of the 3 for the power. So I'm going to do to the 1/3 power on both left and right. The cube root of 870 is 9.5. Again, I didn't put an equal sign here because it's 9.5 times larger than Earth's. Saturn is farther out than Jupiter. It is 9.5 times farther out than Earth. And if I go back and do the ratio t squared to r cubed, I get 1 and 1. I'm going to get 1 for all of these values because they're all orbiting the same sun. Even if it's an unnatural satellite, one that's placed there by humans instead of placed there by chance in millions of years of collision, right? So this satellite is being placed at a radius that's half the distance of Earth to the sun. So I'm putting in 0.5. T squared is proportional to 0.125. And taking the square root of both sides, the time period is 0.35. So think of this as shorter than a year. It's about 35% of 1 year. So 0.35 times shorter than 1 Earth year for this satellite to go around the sun. Halley's Comet, however, has a very long time period and a very elliptical orbit, which you'll see on the next page. Doing the 76 squared gets me 577 on the left is proportional to r cubed. We're going to do that cube root on each side. Last time I wrote it as to the 1/3 power because that's actually pretty easy to put into your calculator. In fact, if you have trouble putting this in your calculator, how about I write out what to type? This is 5776. Use the power button. It's in the right side of your calculator if you're using a graphing calculator. And sometimes if you do 1 divided by 3, it thinks you're doing to the first power and then dividing 5077 divided by 3. So if it helps, instead of putting to the 1/3, let's write this as a decimal. That's the same thing as taking a cube root if you have trouble finding it in your calculator. The average orbital radius then is 17.9 times more distant than Earth. So 17.9 times farther. And let's just see if our chart looks consistent. Halley's Comet takes less time than Uranus or Neptune, so it should be at a shorter distance. The satellite is closer than Earth, so should take less than a year. That tracks. Okay, so now we're thinking about a comet. We have the comet right before is Halley's Comet. This one is showing a picture of Kepler's second law. This is one of those characteristic pictures that I want you to know. What this picture means is that the area swept out by an orbit travels equal distance in equal time. Since all of the time periods were equal to 10 days, then these must be all the same. If it helps, you can also picture it this way. Section D is far from the sun. This is like having a triangle that has a large height and a short base. So the area swept out by D is this much. When it gets closer to the sun, though, it has a large base and a short height, so that those two triangular areas are equal to each other. Now, Halley's Comet, it's actually extremely elliptical. When it's close to the sun at its perihelion, It's a distance r away from the sun. But at its aphelion, it's 60 r times farther away. So actually, this is not drawn perfectly to scale. I would need this radius 60 times on the left. But that's really hard to draw out nice and neat, so here we are. Halley's comet proves that orbits are elliptical, and hence proves Kepler's first law that orbits are elliptical. The comet's orbit is fastest when it's closest to the sun. At point D, the radial distance is small, so that makes it have a higher velocity and a greater gravitational force. It has the highest velocity when it's close to the sun, because when it's close, it experiences a larger force due to gravity. Having a larger force means it travels a faster speed. C actually asks that point again. We know that when the radius is close, the gravitational force is big. If you wanted to represent this with equations, you can. The gravitational force between any two objects is inversely proportional to the square of the distance. So if your radius is close, you're dividing by a smaller number, making a bigger force. Graphically, if the radius is small, the force is big. This is that inverse square law. So when the radius is small, the gravitational force is large. All of those point and support and justify the same conclusion. Finally, it's asking, how does the gravitational force change? As the comet moves away from the sun, its radius becomes 60 times larger. So if this equation represents the original gravitational force, then moving 60 times farther out would get 1 over 3,600 times the original force. 60 squared in the denominator means that the new gravitational force is 3,600 times smaller than it was originally. And in the end, this is why it's traveling so much slower out here. The gravitational force is so small when the comet is out past Neptune. The gravitational force is so small that it makes the velocity very small. So now it's traveling this whole big distance at a very slow speed, and it spends much more of its time away from the sun than it does when it's close. Hey, if you're around for the 2061 showing of the comet, you're probably going to be able to see the comet for a few months. While it's close to Earth, you might see the comet for a few months, but then it's going to spend the rest of its 76-year period very far out in the solar system by Neptune and Uranus. Before I head out here, remember to go read the actual Key and Drive, where you'll see these answers and more in more detail. All right, y'all, good luck on your test. Best of luck.